multipath propagation. So, in the wireless telecommunication, multipath is the propagation phenomenon that results in radio signals reaching the receiving antenna by two or more paths. These causes of multiple paths include the atmospheric tethering, ionospheric reflection and reflection from water bodies, and terrestrial objects such as mountains and buildings. The effects of the multipath include constructive and destructive interference and phase shifting of the signal in digital radio communications, such as GSM, that is multipath, can cause errors and affect the quality of communications. So we'll discuss all the related issues in this chapter. So the multipath signals are received in a terrestrial environment where different forms of propagation are present and the signals arrive at the receiver from transmitter via a variety of paths. Therefore, there would be multipath interference causing multipath fading, adding the effect of movement of either transmitter or receiver, the surrounding clutter to it. The received overall signal amplitude or phase changes over a small amount of time. Mainly, this causes the fading. So, multipath is the propagation phenomena that results in radio signals reaching the receiving antenna by two or more paths. The effective paths of the multipath, including constructive and destructive interference and phase shifting of the signal. The parameters of the multipath channels or the power delays profiles are found by averaging instantaneous power delays profile measurements over a local area in order to determine an average small scale power delay medium. Time dispersion parameters. So what do you mean by time dispersion? So the time dispersion parameter properties of a wide band multipath channels are most commonly quantified by their mean excess delay and RMS delay spread. The mean excess delay is the first moment of the power delay profile and is defined as the where AK is the amplitude and is the excess delay, PTK is the power of the individual multipaths signals. The RMS delay spread is the square root of the second central moment of the power delay profile and is defined as the tau is equal to epsilon a square base k t base k divided by epsilon a square base k, that is equal to epsilon p into t base k into t base k divided by epsilon p into t base k, where ak is the amplitude and is the excess delay and PTK is the power of the individual multipath signals. The RMS delay spread is the square root of the second central moment of the power delay profile and is defined as sigma of base tau is equal to root of tau square minus 2. And now coming to this, where these delays are measured to the relative first detectable signal arriving at the receiver at a tau t0 not is equal to 0. Typical values of RMS delays spread or on the order of the microseconds in order to mobile radio channels, in order to the of the nanoseconds in order of the radio channels. Note that the RMS delay spread and the mean excess delay are defined from single power delay profile, which is the temporal or a spatial average of the consecutive impulse response measurements collected and averaged over a local area. Typically, many measurements are made at the many local areas in order to determine statistical range of the multipath channel parameters for a mobile communication system over a large scale area. The maximum excess delay of x of dB of the power delay profile is defined to be the time delay during the which multipath energy falls to x dB of the maximum multipath. And the figure illustrates the computation maximum excess delay for the multipath components of 10 dB of the maximum. You just see minus to 0 to 50, 100, 150 the excess delay, and then 0 to 10 and minus 10, 20 of 20, where it represents the RMS delay spec, the maximum excess delay, and the threshold delay. And maximum excess delay will be lesser than 10 dB, threshold dB minus 20 dB. And then values of the time dispersion parameters also depend on the noise threshold, level of the power below which the signal is considered as the noise. In practice, values of the depend on the choice of the noise threshold uses the process of the P of T. The noise threshold is used to differentiate between received multipath components and the thermal noise. If the noise threshold is set too low, then the noise will be processed as the multipath. thus giving a rise to the values of the T, P, and then artificially high. And the coherence bandwidth, when coming to the coherence bandwidth, we see it is a measure of the range of the frequencies over which the channel can be considered flat. That is, channel passes all the spectral components with equal gain and the linear phase. It is a definition that depends on the RMS delay spread, where two sinusoids with the frequency separation greater than BC are affected quite differently by the channel. If we define coherence bandwidth BC as the range of the frequencies over which the frequency correlation is above 0.9, therefore BC is equal to 1 by 50 sigma. Sigma is the RMS delay spread. If we define coherence bandwidth as the range of the frequencies over which the frequency correlation is above 0.5, then this is called 50% coherence bandwidth, where BC is equal to 1 by 5 sigma square tau. And coming to the Doppler spread and the coherence time. So coming to the Doppler spread and the coherence time, Doppler spread and the coherence time are the parameters which describe the time varying nature of the channel in a small scale region. So the measure of the spectral broadening caused by the motion Doppler spread of PD is defined as the maximum Doppler shift, where Fm is equal to V by lambda. If the baseband signal bandwidth is much greater than PD, then the effect of the Doppler spread is negligible at the receiver. The coherence time is the time duration over the which the channel impulse response is essentially invariant. If the symbol period of the baseband signal reciprocal of the baseband signal bandwidth is greater than coherence time, then the signal will distort since channel will change during the transmission of the signal. The Doppler spread and the coherence time are inversely proportional to the one, that is Tc is equal to 1 by Fm. In other words, the coherence time is the time where the time duration over which two received signals have a strong potential for amplitude correlation. If reciprocal bandwidth of the baseband signal is greater than the coherence time of the channel, then the channel will change during the transmission of the baseband message, causing the distortion of the receiver. The coherence time is defined as the time over which the time correlation function is above 0.5. Then the coherence time is approximately given by Tc is equal to root of 6 divided by 16 pi square F, that is equal to 0.423 divided by F. So, and coming to the types of small scale fading. So the types of fading experience the signal through a mobile channel depends on the relative between the signal parameters, that is bandwidth, symbol period, the channel parameters, RMS delay spread and Doppler delay spread. Since we have 4 different types of fading, there are flat fading effects due to the multipath time delay. One is the flat fading, such as the fading occurs when the bandwidth of the transmitted signal is less than the coherence bandwidth of the channel. Equivalently, if the symbol period of the signal is more than RMS delay spread of the channel, then the fading is flat fading. So we can say that the flat fading occurs Bs into Bc. The Bs is the signal that bandwidth, Bc is the coherence bandwidth also. And coming to the frequency selective bandwidth fading. Frequency selective fading occurs when the signal bandwidth is more than coherence bandwidth of the mobile radio channel, or equivalently the symbols during the signal is less than the RMS delay spread. That is what Bs into Bc. So we'll stop here and we will check with the other things in the